welcome to our next video. This is the first video of our physics chapter, and today we're going to explore motion together. So a quick refresher about unit conversion. You haven't seen this since chapter 1, so it may be a little unfamiliar to you, but as you're probably aware, units come in a lot of different varieties. So you have our units of pounds and feet and inches and stuff, liters, gallons, and of course you have the metric system, and most science is done using the metric system. And even within the metric system you may want to convert between, say, a gram to a kilogram or what have you, and this is done by converting between units in a cross-canceling sort of fashion. So basically you're building small fractions and you're canceling units like you would in a problem where, say, there was a 2 in a numerator and a 2 in a denominator, two fractions that you're multiplying. You could cancel those 2's. We're doing somewhat similar with units though. So let's say I want to turn 5 meters per second into kilometers per hour. I'd start out by looking at 5 meters per second, and then I'm going to build a series of fractions to get to the units I want. So there's 60 seconds to 1 minute, so seconds would cancel with seconds. In 1 minute there's 60 minutes, or sorry, in 1 hour there's 60 minutes, so your minutes cancel out. And finally I need to get rid of meters, so I'm going to go into kilometers, and in every kilometer there's 1,000 meters. So it's a bit tricky. There's charts, and you're going to need to memorize a few conversion factors on a handout that I'll show you later on. But if you were to multiply these all together, you would find that you have 5 times 60 times 60 times 1 kilometers over 1 times 1 times 1 times 1,000 hours. And when you do that out, you eventually get to, this is 18 kilometers per hour. So not too hard. Probably the scariest part of this is it's fractions. Ooh, scary. But realistically, yeah, this is the easiest way to convert from one unit to another, and you can go out quite far. I remember in my physics class, my teacher had this thing about furlongs per fortnight. So that was actually a problem we had, was we were given a regular unit and we had to turn it into furlongs per fortnight. And a furlong, it has to do with how far, like, ox will pull a plow, and a fortnight is 14 days. So yeah, that was a lot of numbers. Meters per second to kilometers per hour, much nicer problem. Now, since we're talking physics, there's an equation, you probably call it dirt, distance equals rate times time. And dirt is a big important thing that we're going to need here, because really the topic of today is motion. So if distance equals rate times time, I could divide by time on both sides of the equation and solve for rate, and find out that rate is equal to distance divided by time. Now that's going to come into play a little bit when we get into a position type graph. So if we were to graph someone moving away from a reference point, then the slope of that line would be rate. It would be unit distance over time. Remember, rise over run, you can guess which of these is going to go on the y-axis, which of these is going to go on the x-axis. We'll get there in a bit. We'll talk about that a little bit more very soon. The units of rate are always given as length over time. So meters per second, kilometers per hour, feet per second, miles per hour, all these different ways of measuring rate. Alright, your average speed is a scalar value, so it doesn't have any direction attached to it. And really is just your total distance that you travel divided by the total time you traveled. So this is generally not reflective of the actual speed you were going at any time in your trip. It could be. I mean, you could work the numbers just right, but usually you're like slowing down your stop and you're going faster. You could actually work this in some interesting ways. I really doubt police would really be happy if you're like, hey, you know, my average speed was within the speed limit. I was just speeding. I was going 100 miles for a little while there, but I decided to go 35 for a while, so it all averages out, yeah? Doesn't really work when you get pulled over. Definitely never make that joke to a police officer. They will not find it funny, ever. So the actual speed you travel is rarely your average speed. But if I wanted to find an average speed, let's take this situation here. We're going to go 3 miles for the first 2 minutes of a trip, and then we're going to slow down. And we're going to go 2 miles over 5 minutes. So what would be the average speed in miles per minute? And we're going to practice a little bit with unit conversion again and try to turn that into miles per hour. So you have 3 miles plus 2 miles. So the total distance I traveled is 3 plus 2. The total time I traveled would be 2 minutes and 5 minutes, or 2 plus 5. So pretty easy math here. We got 5 miles every 7 minutes. If I were to take 5 miles per 7 minutes and convert that into minutes per hour, I would find that I was actually traveling 42 6/7 miles per hour. Now, I honestly prefer fractions for answers. Probably some science teachers are going to ask for decimals. I prefer precise answers. I think that's the math teacher in me. As your math teacher, I want reduced fractions. I want simplified fractions, but I'd rather us leave off the imprecision that comes with calculating out the decimal equivalent of a fraction. That really doesn't work for me. So leave her as a fraction. Think of it this way: a fraction is a decimal problem you didn't have to solve. Yeah? You could skip a whole step of division there. Alright, so obviously average speed, not super useful, because it doesn't really describe reality. It can give you an impression of how fast you were going over your total distance traveled, but rarely is that reality. So an instantaneous speed, that is what your speed is right now. So if you stop for traffic, if you change speeds in a different area, whatever it is that's going on, the cheetah that's pictured here probably was at rest and then starts going, and there's a point where maybe it slows down or something like that. So we're seeing the speeds at all the different points in time. Basically just clicking in. Are you going 58 miles an hour? Okay. Are you going 60 miles an hour? Okay, now I'm going 35 miles an hour. The average speed is going to wipe away all those changes and just give you this average number that's not real in any way, shape, or form. But your instantaneous speed is always real. It's what's your speed right now. And next we could talk about velocity. So velocity is related to speed. Velocity is the vector version of it. So remember, in a vector we have distance or direction and magnitude. Okay? So velocity is very similar to displacement, which was the first vector we were talking about in class. And since it's speed with direction, it's going to come in forms like, going 50 miles per hour east, going 35 miles per hour southwest. Okay? So we have some sort of direction attached to the speed I'm going, which is important for a variety of reasons. There's a big difference in going 50 miles north and 50 miles south. They're going in opposite ways. So chances are, if you're going fast, you're trying to go somewhere fast, and that somewhere has a direction from a reference point. Okay? Because vectors have magnitude and direction, the change in velocity could occur by going faster or slower, which would be a change in magnitude. while you could also change things up by changing your direction. So there's two ways to alter your velocity. Okay? You could slow down for traffic or a stop sign or whatever, speed up because you got on the freeway. All those are very obvious changes in vectors, and you would describe that by drawing a longer or a shorter arrow. Whereas if you change direction, you're basically going to change the angle that the vector is pointing. And usually you get into this whole degrees, minutes, seconds sort of thing, tied into longitude and latitude, if you know anything about that. We won't go that far. That's very difficult math. That's a little more trigonometry, algebra 2-ish. So we'll leave that off for now. But just understand, realistically what we're saying is instead of pointing up, we're pointing left, right, down, we're somewhere in between when we say we're changing our direction. And now for calculating slopes. We pretty much know this. We have spent a lot of time in CPM talking about how to find a slope. So you should know that it's rise over run, obviously, which is also the change from y over change in x. So delta y over delta x is a way we've been describing rise over run. That's actually used a lot by physicists. Delta y's and delta x's. Delta t, change in time. Delta, remember, is the symbol for change. There's no difference, honestly, between what we're about to do here and what we do in math class. It's one and the same. Math is essentially the language physicists speak. You'll find that, especially when we start talking about Newton's laws, I'll just say F equals ma. And you'll be like, what? But that has meaning to me because I speak math. And hopefully, with the level of CPM we've been doing and getting into a lot of these deep thinking problems, converting sentences into mathematical expressions, you can kind of start to talk like that a little bit. That's a real sign of mathematical maturity. But yes, ultimately you are making slope triangles, you are going to be finding rise over run, and that's actually going to be very, very significant here as we start getting into some of the graphs that go on. I would describe this as physics as looking at the physical world with mathematical eyes. That to me is really how a physicist works. Is you're looking at this world and you're looking at the underlying laws that govern how things move, how gravity works, all these concepts, and how forces work and act, and how energy works and act, and you're basically taking math to that. And that's really the beauty of math and physics, and probably the difficulty of physics as well. So let's start off with looking at distance versus time. Okay. So a distance versus time graph would show you how you are moving away from a reference point. So here on this graph we have a point A, it's at the origin, and a person is driving away from A, and notice that the line has a positive slope. Rise over run is positive as I'm moving away from A, because I'm increasing my distance as time passes. Okay? And then you come to this plateau, and my distance stops changing. That means that I'm not moving away from A, I'm standing still. So this person may have started at their house and they got dropped off at Granite Oaks. And now they're in class. They're not really moving from this location. They're staying fairly constant. If Mr. Phillips was in room E1, this would pretty much be you throughout the day. You just hang out E3, E2, E1, you know? Most of your motion comes into going to A4. And then eventually, at the end of the day, 310 comes, and we get to come back. We get to go back home. and this person is got a decreasing slope because distance is going down until they finally return to point A after some time. So we have an increasing slope giving us a positive or increasing positive slope, moving away from that reference point. The larger my y value is, the farther away I've gotten from that reference point. That's a kind of a key concept. So if my y value were 100 miles from, and my reference point was in Rockland, then we might be talking about having gone to San Francisco. Okay? So the y value in this case has significant meaning in the form of distance from that point A. So the slope, what it means is how fast I'm going away. So if I had a slope that was going up 3 miles every 5 minutes or something like that, 3/5 slope, then I'm moving away at a certain speed. But if I were moving away a mile every minute, that's a faster change, that's a faster slope. Okay? So the steeper the slope, the faster you're getting away if it's positive, or the faster you're going towards if it's a negative slope. Okay? So a slope of -2/1, if this were in miles per minute or something like that, would mean that you're going towards this every 2 miles for every minute that you travel. Okay? The rate at which I move away from a reference point is my velocity. So that's the slope of those lines was literally my speed. Okay? The way I changed position given time. But velocity itself could also be graphed. Okay? Now, this shows me how fast I am moving with time. Okay? So if I look at this graph here, I see that on my y-axis is my velocity. Okay? So I started out with no velocity here at time 0, and then I start doing what's called accelerating. Okay? Your acceleration is the slope of the graph of velocity versus time. Okay? The acceleration is the slope of a velocity versus time graph. Alright? If my slope is positive, I am accelerating, which means that this car is speeding up. So for the first region on this graph, the slope is positive and the person is going faster and faster away from the reference point. And then they hit a constant velocity where it levels out. And that means that their speed stayed the same. So think of it like this. Maybe you are pulling out of your driveway, you're accelerating, you're going faster and faster, and somehow your house happens to be right on the on-ramp for a freeway. And so you're speeding up, you're speeding up, you're speeding up until you hit a certain point, and then you sustain that particular velocity for a good long time. Okay? And then afterwards, you start decelerating and slowing down. You're slowing down, you're slowing down. You have a negative slope to your graph. Keep in mind, when you're constant velocity, you have a 0 slope to your graph. Okay? So as I decelerate, as I slow down, I stop going so fast, eventually I come to a point where I have no velocity at all. Okay? And that ultimately means that person's no longer moving. Now, the units for acceleration, which again is the slope of a velocity versus time graph, are a little tricky. You've actually seen them in a couple of the problems that we've done. So acceleration is the slope or the rate of change of velocity. Ultimately, that makes it the rate of change of a rate of change, because remember, velocity itself is how fast you're moving away from a point. Okay? The units on that end up being distance over time versus over time. And if you simplified that out, you would actually have distance over time squared. So oftentimes you'll see things like meters per second squared. They've kind of worked that out there in the picture. Any distance over time squared is an acceleration. Okay, kilometers over hours per second squared would be how fast your kilometers per hour are increasing every hour. Okay. Usually meters per second and meters per second squared are the ones that you tend to see the most. Your average acceleration, therefore, is what your final velocity is minus your initial velocity divided by time. And this is actually the math problem that you're going to end up working with the most as far as all these things go. So a sample problem here is, let's say there's a hockey puck, and it's going to take about half a second to reach the goal. And the puck starts at rest. The guy has got his hockey stick, and the puck's right in front of him, and he whacks it. And in half a second, it reaches a final velocity of 40 meters per second. So what is the average acceleration here? Well, you very simply take the final velocity, you subtract the initial velocity, and this is the tricky part. The puck started at rest. At rest is your initial velocity. At rest means 0. It's not going anywhere. Okay? If the puck had started at 5 meters per second, I would make that a 5. Okay? And I'm dividing this by the half second that it took to reach the goal. Okay? And 40 divided by 0.5 turns out to be 80 meters per second squared. That's probably the most difficult part of this, is remember that the units are length over time squared. So be careful with that. One quick note, obviously, from this conversation we've had, you probably can see that there's some sort of relationship that exists between the graphs of position, velocity, and acceleration. And this kind of summarizes it a little bit. So let's say there's an object that's just not moving. It's stationary. So the object is not going farther away from where it's located. It's just hanging out at the same spot. Your velocity then would be nothing, which means you're not accelerating either. So here on the stationary object graph, we see that you have a horizontal line for your position, and you have a horizontal line of x equals 0 for both your velocity and your acceleration. Now, let's say I was moving linearly. Okay, so I'm linearly increasing my distance from some reference point. Not speeding up in any way, I'm not slowing down, I'm just moving away from it at the same rate of change, right? Moving linearly away, then my acceleration or velocity actually would be constant. Okay? My speed isn't changing. I move at the same slope every point of time on that uniform motion graph. And because my velocity is not changing, my acceleration is the line x equals 0. Okay? Now, if somehow I was moving away from a place as a quadratic, moving away as some sort of x squared term, in this case time squared, since the x-axis is time, then something crazy happens. My velocity would become a linear function. Okay? So if I'm moving away from, my position is changing quadratically, my velocity is changing linearly, and my acceleration becomes a constant value. Okay? That relationship you will study if you go far enough in math. And that's actually a very, very important relationship right here. And that goes into calculus, ultimately. We won't do much with this, obviously, because to really dig into that relationship, you need to know a lot more math. But you can see that relationship, and you are responsible for noticing and understanding these three graphs situations and how they relate. So I may show you the graph of, say, a stationary object or a motion with constant acceleration situation, and ask you to draw reasonable graphs for these. So you probably want these in your notes if you haven't put them there already. There's another relationship. Were you to take that velocity graph and kind of drop a line from the end of your graph at whatever point you want to end it down to the x-axis, you would basically make one of these various shapes here: rectangles, triangles, trapezoids, or a complex shape. You got to kind of cut into pieces. You could find the area under the curve, as they call it, or just find the area of this object that you've now created, this geometric figure. And if you were to find the area under the curve of a velocity graph, you would actually find the total distance you traveled. Okay? If you think about the relationship I just showed you with how the graphs of position, velocity, and acceleration are related, this kind of feeds into that same relationship. It's just going kind of reverse of what I was showing you before. This is explored really in depth in later math classes. Again, this is part of calculus. But definitely that triangle, the 1/2 base times height, will be showing up as an extra credit question on our motion test. It's very reasonable, I believe, to ask you to do 1/2 base times height. You may not understand the deeper relationship of how that gives you position, but you can at least accept that it does, because that actually is truth. And if you want to see how that works, I can do you a little demo at some point, and hopefully that'll clear it up if you're a little confused. But 1/2 base times height on a linear velocity function there, we just find the area under that curve, and that's going to tell you how far you went, because each little segment there, the line itself represents how fast you're moving away, and time represents how long you're going that far. So literally every bit of that area is you traveling a certain speed for a certain amount of time, and that brings you right back up to how far away from something did you get. Okay, so this question will exist. It is extra credit if you don't quite understand this. The way you solve it is you just find the area. Okay, 1/2 base times height. Pretty simple problem we do all the time. Let's see if you can take that and apply it to this situation. Okay. So let's do a quick wrap up. Position is how far away I am from a reference point. Okay. So there's some place, be it home, be it Granite Oaks, be it whatever reference point you want, and you want to see how far you are from that place. If you were to take the slope of that particular graph, you would find out how fast you're moving. Okay, and you could actually graph the slopes basically. And if you graphed all those slopes, you would have a velocity versus time graph, and that would show you how your speed is changing with time. And if you were to look at the slope of that particular graph, you would find acceleration graph. And acceleration is how fast your velocity is changing with time, and that too can be graphed. Interestingly, the jerk it would be the slope of the acceleration. And that's like, you probably experience jerk as you're driving, being like pulled if you're going on a curve too tight or on a roller coaster or something like that. But yeah, that would also be another one of these. Take the slope of a graph, find something new. So those of you who've ever asked the question to a math teacher of, why do I ever need this when you're doing lines, this is a huge reason why. This is beautiful, beautiful math, and it's a very clean application of slopes and why that's important to us. Hopefully, the take home here is that you at least understand that position, velocity, and acceleration are all related. They're related by the fact that they're rates of change of each other. Okay. Hopefully that makes sense, and we're going to use this principle to play with some Connects cars. So that sounds like a lot of fun to me. Hopefully that sounds like a lot of fun to you, and I'll see you in class on Wednesday. Bye.